All right, y'all. Now we're going to do problems 1A and 1B together, hash table insertion. By the way, if you're staring over here and you're kind of alarmed, pretty much what happened is I was uploading the video from last quarter for this problem, and I realized at approximately 3 a.m. that there was a huge mistake in that video that we did not notice. So, yay, I get to re-record it. Hopefully it shouldn't be too bad, though. So that's why, if you're concerned for me, don't worry. I promise I don't do this too often. But yeah, let's go ahead and do this problem together. So problem 1A, right? So 1A is a pretty mechanical problem, right? We have a hash table with 10 buckets. We do not resize it, right? And this is our hash function, right? Just 4 times our key, because you'll notice all of these keys are actually numbers, right? So again, this is our hash function, and we have 10 indices or buckets. So we're going to insert all of these into our hash table. And the thing I really want to emphasize, right, is we are going to hash with the key, not with the value. This is something really common that students mess up, right, kind of understandably. It's the key, right, that tells you where to go inside the table. All right, let's do these. So 1A, our first key value pair. So 1 is our key. So this is what's going to tell us, right, which index we end up at. To figure that out, though, right, specifically, we're going to take our key of 1. We're going to apply our hash function to it, right, which is just multiplication by 4. And applying our hash function to our key of 1 actually gives us a raw hash output of 4, right? So, we can actually kind of go ahead and use this as our final index, right? But technically what we do, right, is after we get this final hash output, we also call that a hash code, right? Once we get that raw output, we actually mod it by the number of buckets, right? And then that's our final index. Technically here, right, doing this mod doesn't actually change, right? Like 4 mod 10 is still 4. But later this mod's going to be super important. Just to remind you too, the reason we do this mod is, if this raw hash output's like a really big number, like let's say it was like 10 gajillion, I'm not even sure that's a real number, but let's say it was like a really huge number that was like bigger than the number of buckets we had, right? Doing this mod is actually going to make sure that like this is a valid index. But yeah, that's the process. We're going to do that for every single key value pair. Just to recap, hash your key, in this case 1, to get a raw hash output. Take that raw output, mod it by the number of buckets, and that's your final index. Once we go through that entire ordeal, right, for this key of 1, we find out that our final index is 4. So that's where our key value pair 1A lives. Moving right along, 4B is our next key value pair, right? Same process. I'm going to hash this key of 4, right, to get a raw output of 16, right, because 4 times 4 is 16. And then I'm going to take this raw hash output of 16 and mod it by the number of buckets, 10, to get a final index of 6, right? So here this mod actually does make a difference because I don't have an index 16 here, right? But I do have an index 6. So again, this is our final index, right, of 6. So 4B is going to go over here at index 6. All right, chugging right along, 2C, our third key value pair. Same process, right? If I hash 2, I get a raw output of 8, right? If I then mod 8 by the number of buckets, 10, I still get 8. So 2C goes at a final index of 8 over here. All right, 17D. This is the first time that something kind of spicy happens. I hear that kids use the term spicy. I don't actually know. I'm like internally very old. But we take 17, right? We hash it to get a raw hash we hash it to get a raw hash output of 68, right? Because 17 times 4 is 68. And then we take this raw output, we mod it by 10, and we get 8 as our final index. So eagle-eyed viewers out there may suddenly realize, hey, there's already a key value pair, right, at index 8, right? We added 2C like a while ago. But now I'm going to try to put 17D at index 8 as well. Like, is that okay? Will the computer explode? Luckily, everything is okay, right? This is something called separate chaining that Casey covered in lecture, right? All separate chaining means is when you have literally this situation where two key value pairs go to the same bucket, right? Like they don't have to like fight each other to the death to figure out like who goes at this index, right? They can both coexist together. And the way that we do that is we just start a linked list at this index or bucket, and it contains all the different keys, right, that map over here. So TLDR, right, 17D will also map to index 8, but because we started a linked list here, right, like they can coexist together in that list. Life is good. All right, 12E, very similar, right? If I hash 12, right, I get a raw hash output of 48, because, 4 times 12 is 48. And then if I mod that raw output by 10, I get a final index of 8. And 12E also lives here, right? So just like 17 and 2 kind of, lived together in this bucket before, now 2, 17, and 12 now, right, are all going to coexist as keys at index 8. All right, 9E, very similar, right? I'm going to hash 9 to get a raw output of 36, right? I am then going to mod 36 by the number of buckets 10 to get a final index of 6, right? And just like we handled collisions right over here, we're going to handle them over here as well, right? When I try to put 9E inside this index, 4B will already live here. But again, there's no fighting, there's no overwriting that happens here, right? Because these are two different keys. They just kind of live together in this linked list. 19F is very similar, right? If I hash 19, I get a raw output of 76. If I then mod that by the number of buckets 10, I get 6 as my final index. So 19F joins the party in this linked list. All right, 4G. This is the most important part of this problem, 1A, I think. So 4G, right? The process for inserting this is the same as everything else. I'm going to hash 4, get a raw output of 16, and then mod that by the number of buckets 10, right, to get a final index of 6. So here's something that you need to know. A hash table is just a dictionary, right? It's one way that you build a dictionary. In a dictionary, you cannot have duplicate keys. That is just like a fact, right? Like we cannot have 2 4 keys at this index, because that would just be a violation, right, of that rule. Every key is unique. So because of that, right, I can't have like my old 4 key up here and then also add like my new key value pair 4G down here or something like that. What I actually have to do is I will go, right, to this old key value pair that involved 4 as my key, and I will overwrite, right, or I guess update's a nicer way to say it, right? That sounds less aggressive. But I will overwrite or update this value here from its old value to a new value of G. So that's how I handle insertion, right? I don't have 2 4 keys here. I go to the old key value pair with 4, and I update its value to be G now. So this is probably the most important part of this problem, right? Like whenever you insert, right, a key twice with a new value, you actually update the old value to the new one. You don't have duplicate keys. All right, 8C, right? If we insert this, it's pretty much the same process, right? Hash 8 to get a raw output of 32, mod by the number of buckets 10 to get a final index of 2, and 8C lives over here. All right, last one, 12F. If we hash 12, we are going to get a raw output of 48, right? If I then take my raw output and mod it by the number of buckets 10, 8 is my final index, right? And now we're going to be in a very similar situation to 4G, right? When I go to index 8, I'm going to be like, holy cow, right? Like, there's already a key 12 here. What do I do, right? I can't have 2 12 keys, right? Again, for the same reason that we saw here. So I'm just going to go to 12, right? Go to this key value pair and update this value from its old value to a new value of F, right? And that's 1A. Hooray. Feel free to pause or go back if you were confused about that. I'm going to chug through 1B now. So 1B is kind of cool. It's actually pretty mathy. So the idea with 1B is like, hey, let's use this hash function that we were using in 1a. But now instead of 10 buckets or indices, right, I have 12. Could there be anything wrong with this, right? Is anything funky going to happen? So to see if anything funky happens, let's just start counting keys up from 0 and see where they would go, right? So where would 0 go? Well, 0 times 4 is 0. Cool. Mod 12 is still 0. So 0 goes to index 0. All right, that makes sense. What about a key of 1, right? We're just counting up here, y'all. Well, 1 times 4 is 4. Mod 12 is 4. So 1 goes to index 4. Cool. What about 2, right? Just counting up here. Well, 2 times 4 is 8. Mod 12 is still 8. So a key of 2 goes at index 8 down here. All right, nothing catastrophic has happened yet. It's really when we get to 3 that like everything kind of hits the fan, so to speak. 3 times 4 is 12. That's actually our number of buckets, right? So 3 times 4 is 12, mod 12 is 0, and oh no. 3 has snapped back to the same bucket that 0 lives in, right? Both 3 and 0 here live at index 0 over here. And actually, more horrifyingly, right, if you keep counting up, this will just keep happening, right? So 4, the next number, right? 4 times 4 is 16. Mod 12 is 4. So 4 and 1 actually map to the same bucket 4 down here, right? Similarly, 5, right? 5 times 4 is 20. Mod 12 is 8. So 5 and 2 actually get mapped to the same bucket down here. And no matter how many times you keep counting, right, you will see this pattern where only buckets 0, 4, and 8 end up getting used. We have 12 buckets, right? We should be able to put stuff in, but only the 3 circled ones that you see here are actually getting any use. So here's my meme to reconnect with the youth and kind of express what's going on here. I don't know. I hear that Zoomers like PewDiePie. I wouldn't actually know. I'm too old for that. But yeah, so this is pretty much what, like, literally what I just said, but in other words. So why is this bad? So this is bad because key value pairs that would have been spread over the entire array, right? Instead of being spread over all 12 buckets, they're kind of being shoehorned into just these 3. That's really bad because it means that all 3 of the linked lists, or the chains, right, at these 3 indices are going to be super long, right? Because they're the only indices being used. And one thing you should know about hash tables, right, is the runtime is proportional to how long those chains are. So a super long chain, like the ones you would get here, that's going to give you really crappy runtime. So this is very frowny face, right? We don't like this. So really, right, the kind of original sin that caused all of this is when we got to 3 here, right, and we did, 4 times 3, we got 12, our number of buckets exactly. That kind of snapped 3 back to the same bucket as 0, and then it kind of started this pattern from hell, right, where we're only using these 3 buckets. So to prevent that, right, because, in other words, right, our problem popped up because 4 was a factor of the number of buckets 12. To prevent that, well, just pick a prime number of buckets, right? Because then, 4 will never be a factor of a prime number of buckets, right? You'll never be able to multiply 4 by anything to get a prime number of buckets, right? By definition of a prime. So you'll never have this sort of snapback behavior that we saw with 3. So TLDR, right? This happened because 4 was a factor of our number of buckets, right? Because we did 4 times 3 and got 12 exactly. And you can prevent this super easily by just making your number of buckets a prime. We also didn't cover this in section. If you just want to see what we did in section, you can literally tune out now. But for those of you who are still watching and are curious, right? One of my students actually asked a really good question in section, which was like, we can make the number of buckets prime to start, right? But then when we resize, what happens, right? If I double, I may not have a prime number anymore. So this is actually kind of like a fun fact that happens in C++ and other languages, right? When we upsize our hash table, right, because of our load factor, you actually have to find the next prime number that's about 2 times the one that you're at for your hash table size. So just to kind of like make that clear, this is something that people do like in real life, and it has like implications for things like resizing. If that didn't make any sense to you, don't worry at all. Just know that like generally, right, when you have hash functions that look like this, you want to have a prime number of buckets to prevent the situation you see here. Cool, that's 1A and 1B. That's all I got, y'all. Stay safe and enjoy the rest of the playlist. I don't think there are any mistakes in those videos. Please post on Ed if there are, but I'm gonna go sleep now. Later, y'all.